Alright kids, welcome to your final geometry video of the year. Congratulations on completing your final quiz of the year, but who's counting? Okay, so the next section, sorry, after the quiz, this is not the last section of the year, this is just the last video. 14.6, it's about what happens when we do more than one transformation at a time. So we're done learning about all the possible transformations that we're going to study this unit with reflections, rotations, translations, and glide reflections and dilations. And then now it's about, well, what happens if we do more than one? What happens when they combine? The symbol for combining them is this little guy right here. Whoops, just a little O symbol. Looks like a little O. It stands for composition. You might have seen that in algebra. They combine functions in algebra, and we'll talk about that later down the page here. But that stands for composition, or composed with. The tricky part about it, when we say something like this, reflection over x composed with a reflection over y of point A, whoops, sorry about that, I don't know what that is the tricky part is which one we're supposed to do first, because it does make a difference which one goes first. If you reflect over one line and then another, it might make a difference if we reflect over the x-axis first or the y-axis first. Sometimes it does matter, sometimes it doesn't. Kind of like in algebra, some operations are commutative and some aren't. What is this doing here? Can I get rid of that? Oh, I do that, it goes away. All right, so what's tricky about this notation is that the one that's closest to the point, the one that's on the right, is the one you actually do first. And here's kind of an explanation of why that is. If you were to perform this reflection in x and reflection in y of point A, you can think of this little circly thing here, this little composition symbol, as the start of another set of parentheses. And if it looked like this, I don't think there'd be any doubt in your mind that we should do the one that's closer to the point, closer to the pre-image point in the notation first. We do what's inside the innermost parentheses first, and then we work back from there. So this would be reflect A over Y, and then when you get to the result of that, now let's reflect that over X. So reading it, seeing it this way looks kind of backwards, because it means do this one first and then do that one. You can think of it like this, it means the same thing. All right, then I've got some examples of that down here. Of course, you can read this. But if you were to see this little thing right here, it would mean, okay, we're going to start with pre-image A. The first thing we're going to do with it is dilate it from center O by a factor of 2. And then once we get to that image point, we will take that and put it directly into this transformation, which is translate by vector BC. We'll do that in a real example in a minute. There's some examples in the book of this where they just do it completely in algebra. So I made up a little function here, made up an f of x that's 2x minus 7 and g of x, which is 3 over x. And then just did some algebra demonstration here of what happens if you do f first, what happens if you do g first. This, of course, would be g first. This one would be f first, because, again, we're kind of reading that backwards. The one closer to the pre-image is the one you do first, and then you kind of work backwards. So, yeah, I try it with putting a number in, but I also tried it with the general formula. If this is, why does that thing keep showing up? What if I just use this? Okay, fine. Sorry, I don't make these every day. The function rule, if f of x is that and g of x is this, we could talk about, well, what's the generic rule, or what's the overall rule for what's happening to x if it goes into the g machine and then that output spits directly into the input of the f machine. We're going to get what kind of function from start to finish. This is what would happen to x. We would put x into g first, and it would spit out 3 of x. Then 3 over x. Then 3 over x goes in for actually what x used to look like over here. So it would be 2 times 3 over x minus 7. So as a function, f of g of x, you can read it that way, f of g of x will always do all of this. G of f of x, if you follow that the other way, looks completely different. So it does matter which one comes first. G of f and f of g are not necessarily the same thing. Or if you need to find image points of those things, you can simply take a number, like here I operated on 5, put 5 into f of g of x, which means we're going to find the f of g of 5. G of 5 is something you're used to finding, and g of 5 would be 3/5 here. Whoops, sorry, jumping around again. And then f of 3 over 5 looks like that. And just so you can see it also, g of f of 5 turns out completely different. Okay, and you could even do this with pre-images. Again, that would be really tricky. You could track, they could give you a number like this and say, okay, what's the image, what's the pre-image of 1 through all of this also. You just have to run that whole thing backwards. But I get bogged down with these algebra examples. These algebra examples just appeared in our book because they're trying to get you to attach this knowledge to something that you've learned before. I don't know if it's that helpful for everybody. Anyway, you can read that if you want. We like to live in geometry. All right, so here's that first example I was going to talk about. So we're going to take this figure triangle PQR, and we are going to perform this composed two transformations on it. We're going to dilate it by reading this carefully, and then we're going to dilate it first, and then we're going to translate it. Here's the vector BC. You could say we were going to translate by vector BC and just show the vector BC, or I could say here's the translation. It's this kind of coordinate translation. Let me do this on Sketchpad, because it's just so much cooler on Sketchpad if I do it. It's going to be so much more accurate. All right, I'm going to dilate this thing by a factor of 2, centered at 0, 0, which is nice. So it means all these coordinates are essentially going to get multiplied by 2. So if you remember from last section when we did that, I can cheat here on Sketchpad and have it do it for me. Oh, I didn't do the points. Maybe I should do the points so you can see where exactly those are going to go. Transform, dilate, factor 2. They're going to go right there. Are you surprised at where those landed? This Q here was at 2, 4, so it's going to go up here to 4, 8. P was at 2, 1, so it goes to 4, 2, and R was at 6, 1, so it's going to go to 12, 2. Okay, and then dilate, or sorry, and then we dilated, and now then let's all shove it down by this vector here. So I'm going to mark that as the vector, and then if I take this new figure and it's going to go off the page a bit, and then I translate that, it's going to go down there. Let me move this over so you can see it. Can I move this easily? Yeah, okay, look at that. I translated the whole video screen. All right, so everything there went. If you look at the vector, the way it was written out in coordinate notation, also, I took all these points from the dilation. Remember, because I'm operating on successive transformations here, I'm going to dilate and then translate over 3 and down. Looks like down 5. Yeah, so that was the vector over here. So that went over 3 and down 5 and became this thing over here. So really this little intermediate thing is not terribly helpful now. I mean, that's not really the final answer to this question. The final answer to this question is this one down here. I kind of needed this, just like when we did glide reflections. There's an intermediate step you need as a stepping stone kind of to get to the final answer, but this is the image of the entire composition. It was dilated and then it was translated. And that was one of those times where the order does matter. If you were to translate first and then dilate, notice what would happen to point P. It would have gone, in the end, it would have ended up at 10, -8 rather than 7, -3 where we just had it land. Okay, what if, just say, we might want to do 2 reflections that happen to be parallel. Now we're going to start talking about, there are going to be times when performing one transformation and another leads to some very predictable results, and we can actually make theorems and rules and predictions about where those things are going to go. The first one is, well, what if what if there's 2 reflections and the lines of reflection are parallel to each other? Let's look at that on Sketchpad too. All right, again, I'm going to cheat. I'm going to use Sketchpad. The directions there say to first reflect over, do I have this right? Reflect it over, oh no, I'm translating when I don't want to translate. Reflect it over U first and then V. Good. That's what I was thinking. Reflect it over U first, then V. So I'm going to mark U as my reflection line, and I'm going to show this reflection. Now, do you know how to do this on pencil and paper without Sketchpad? You should know how to do that. Remember, when you reflect this, you're showing, now forget about line V here for a second. Just reflecting this over U, we make it so, remember, do the thing with the ruler. You measure with the ruler so that has the line of reflection as the perpendicular bisector. Make this dashed, yeah. So all these connections, when you get from A to A prime over here, B to B prime, it just has to go perpendicular so that this midpoint's on the line, and same thing with C. So you're going to reflect it like that first. So I reflected it over U. Now I have to take this thing and reflect over V. So think about where that's going to go. It's going to kind of spin. It's like we have a triangle on a stick here, and we're going to spin it by twisting around that stick. So forget about U, forget about U. Sounded mean. And forget about this triangle over here. We're just going to reflect these 3 points over line V. So I want to call that my line of reflection, and this point's going to kind of travel on this same little dotted line actually over here, so the midpoint of that connection's on V. The midpoint of this connection's on V, so it's about there. This one's going to have to go this way over here somewhere, so that midpoint's on V. Let me reflect all that. I don't need all this stuff selected. Whoa, come on. I really don't need this. Or I just want the triangle. That's not so bad. All right, reflect that over V. Transform, reflect. Did I select the right line? I did. Okay. So there's the reflection over V. So it should look something like that. Now let's talk about what happens from there to there. Forget about the gray one for a second, and I made it gray for that reason, because it's kind of just our intermediate stepping stone when I needed to calculate the final step after all of this translation. Or sorry, after all of this reflection. Reflecting once, reflecting twice. Just compare this one and this one. Look how they kind of travel together. One of them is just, ooh, I can even move this and it moves the gray one around. But relative to each other, the two brown ones are kind of dancing in a very predictable manner, even if that gray one jumps around a lot. There's clearly, I don't know if it's clear to you yet, but there is a translation actually that takes this one straight over here. And we can make some predictions about that translation. It's a very predictable translation. The translation went like this. It went in a direction perpendicular to the original two lines. So, I mean, all I knew at the start of this thing was I was going to do a reflection over line number 1 and then line number 2. I called them U and V in the sketchpad, in the drawing on the other page. Whenever you do that, you end up just taking from start to final finish point. So again, forget about where the first reflection image goes. From the start to the second reflection image is always just this. It's a translation in this direction, in this amount. Now, what amount is this? It turns out to be twice as far as however the lines were in the first place, apart. Let's go back to the sketchpad here. Yeah, I don't know if you can tell that, but this translation has everything to do with how far apart the lines are. Ooh, I can move the line. Good. If the lines are basically on top of each other, well, that's kind of predictable. This thing is just going to, ooh, too many mice, is going to reflect over the line and reflect all the way back. If the lines have any kind of space in between them, like this, then we start to see a translation of a little bit. And it could be, yeah, they could be really wacky. Look how far this translation goes. So again, I'm reflecting over this little line first, then reflecting this gray one over the line V. And from start to finish, I have a translation. Here's a better picture of that. Here's another sketchpad document someone else made. So if I reflect over, and there's a little one there, reflect over the light blue line first, and I get a light blue reflection. That's very nice. I reflect over the green line, and I'm going to get a green image. But notice that looks the same down here as if I had just gone like this and slid that straight down. How far is this slide? Well, this slide here from D to F is the same as taking this distance between these lines and multiplying by 2. Now, why is it that this is exactly multiplied by 2? Well, if you can see here, hopefully this will work. If I said this, when D reflected and went to E first, whatever distance this was right here, I'll call this A. That's the same distance there. From D to the line and from the line to E is the same. That's part of the definition of how this reflection even happened. That midpoint between D and its first reflection image had to be a midpoint right here. Same thing then when E reflects over and goes to F, however far it is to the line, the green line would be, let's call it B. And that's also the same distance over there because that's what a reflection does. Look at this now. The distance between the lines is A plus B. What's the overall length of how far this thing moved? A plus B plus B. It's 2A plus 2B. Anybody got goosebumps yet? 2A plus 2B, or in other words, it's 2 of that, and that was the distance between the lines. So it's always going to be double. Now that might start to look a little bit different when we move lines around. Let me get rid of those notations because I'm going to start moving stuff. If I start moving lines around in such a way that especially that light blue thing starts zipping all over the place, things start to get weird. Oh, that's going off the screen for you, sorry. Make the lines really close together. Yeah, that first reflection goes off the page somewhere. But so this first blue thing reflects way off here off the page, and then from off the page over green reflects and comes almost all the way back. But that slide that's only that far, that little distance D to F, that's twice as far as this was. Even though, so drawing out the little A's and B's on that looks a little different. It's a different case of the same proof. Or what if I start with this thing way over on this side somewhere? Now everything's off the screen, sorry. Turns out it's gonna end up being the same thing. It's always going to be double. The proof just goes a little bit positive and negative, wonky on a couple of things, but it comes down to the same thing. Since this reflection always works out to have midpoints landing on the reflection lines, that has everything to do with how far the translation is, no matter which sides of the thing it resides on. So the hard part about this, or when you go to do problems about this, you have to start like ignoring what happens to this one. The translation from start to finish really doesn't depend where this thing is. Notice that thing kind of goes crazy compared to the two, but the blue and the green here, sorry, the dark blue and the green here, are kind of stuck together in this one little translation. All right, on to part 2.